We just discovered something on Titan that makes every scientist who sees it go completely silent. I'm not exaggerating. Saturn's largest moon is hiding secrets that violate everything we thought we knew about chemistry, geology, and possibly life itself. And in less than 10 years, we're sending a nuclear-powered drone to find out if what we suspect is actually true. Picture this, a world where gasoline falls from the sky as rain, where mountains are made of solid water harder than concrete, where rivers carve through frozen bedrock and empty into vast methane oceans that stretch beyond the horizon, where snowflakes aren't ice, they're organic molecules drifting down from an atmosphere so thick with chemical smog that you couldn't see your hand in front of your face. That's Titan, and it shouldn't exist. Right now, as you're watching this, there's a process happening on Titan that's destroying its atmosphere. Sunlight rips methane molecules to shreds. Saturn's magnetosphere tears them apart atom by atom. These fragments don't just disappear, they recombine into something far stranger. Ethane, propane, acetylene, benzene, hundreds of exotic compounds that Earth's chemistry shouldn't allow at these temperatures. These molecules grow heavier, more complex, until they form an impenetrable orange haze that swallows the entire moon. Scientists call this haze tholins, vast chains of carbon, hydrogen, and nitrogen locked together in patterns we've never seen anywhere else in nature. And here's what keeps astronomers awake at night. These tholins don't stay in the sky. They rain down, they accumulate, they form dunes that stretch for hundreds of kilometers across Titan's equator. Not sand dunes like the Sahara. These dunes are made of organic particles that look disturbingly similar to coffee grounds. Dead organic material covering a world that might not even be dead. But there's a catastrophic problem buried in all of this beauty. Every calculation we've run confirms the same terrifying conclusion. Titan's atmosphere should have vanished 30 million years ago. That's nothing compared to the 4.6 billion years this moon has existed. The math is simple and brutal. Methane gets destroyed faster than any known process can replace it. Titan's sky should be empty. The surface should be a frozen, airless wasteland like every other moon we've studied. Yet when we look at Titan, we see an atmosphere denser than Earth's. Something is feeding it. Something we don't understand is pumping methane into that sky fast enough to replace what's being destroyed. And if we're wrong about what's happening here, we might be wrong about everything. For years, the leading theory was simple. A global ocean of liquid methane buried beneath the ice, slowly leaking into the atmosphere over billions of years. It made sense. It was elegant. And when Cassini arrived in 2004, equipped with instruments powerful enough to peer through the haze, scientists were confident they'd find it. They didn't find that ocean. What they found instead changed everything we thought we understood about moons. On January 14, 2005, the Huygens probe separated from Cassini and began falling. For 2.5 hours, it dropped through Titan's atmosphere, cameras recording images that made mission control erupt in stunned whispers. The pictures showed pale hills with dark rivers carved into ice, drainage systems that looked exactly like Earth, but wrong, alien, uncanny. When Huygens touched down, it became the most distant landing in human history, 1 billion miles from home, farther than Mars, farther than any asteroid we've ever reached. And what did it photograph? Rocks, scattered across a dark, desolate plain. Except they weren't rocks. They were ice boulders made of frozen water, as hard as granite at negative 179 degrees Celsius. And something had eroded them. Something liquid had worn them smooth at the base, carving patterns that only flowing liquid can create. But at Titan's surface temperature, water doesn't flow. It's harder than steel. The liquid that carved those ice rocks wasn't water. It was methane. Natural gas in liquid form, pooling and flowing across a world so cold that our understanding of chemistry says it should be impossible. And then Cassini's radar started mapping. What it revealed made even veteran planetary scientists question their own data. 3 massive seas near Titan's North Pole, Kraken Mare, so large it would dwarf the Great Lakes if placed on Earth. Ligeia Mare, stretching across 200 kilometers of frozen wasteland. Punga Mare, smaller but still vast enough to swallow entire countries. These aren't puddles, they're oceans of liquid methane measuring 691,000 square kilometers combined, deeper than 200 meters in some regions. And they have waves, currents, weather systems that generate oily methane rain, drenching the surface in liquid natural gas before it evaporates back into that thick, toxic sky. Titan has a methane cycle that mirrors Earth's water cycle in every detail, operating at temperatures that would freeze carbon dioxide into solid ice. This is chemistry that our textbooks say cannot happen. Now here's where things get genuinely disturbing. While Cassini was mapping those methane seas, it was also measuring something else, tiny variations in Titan's gravity field during dozens of flybys. Those measurements revealed something that shouldn't be possible on a frozen moon orbiting Saturn. Titan's shape changes. The entire moon bulges and contracts in response to Saturn's gravitational pull, flexing like a stress ball being squeezed. That only happens if there's liquid beneath the surface. A lot of liquid. When Huygens was descending in 2005, it transmitted radio signals back to Cassini. Scientists analyzing those transmissions detected signatures that could only mean one thing. An ocean exists 35 to 50 miles beneath the frozen crust. Not methane, water. An entire ocean of liquid water mixed with salts and ammonia, serving as antifreeze to keep it from freezing solid despite temperatures that would kill any Earth organism in seconds. In some models, this ocean could be 200 kilometers deep. Read that again. Titan has two oceans. One made of methane on the surface, visible to our cameras and radar. Another made of water hidden deep beneath miles of ice, completely invisible and utterly inaccessible with current technology. But this discovery doesn't solve our original mystery. It makes it worse. If the subsurface ocean is water, where is the surface methane coming from? What force is powerful enough to continuously pump natural gas from Titan's interior into its atmosphere for billions of years? The answer might be the most alien form of volcanism in the solar system. Ice volcanoes, cryovolcanoes that don't erupt molten rock, they erupt slush. Liquid water mixed with ammonia and methane exploding from Titan's interior at temperatures that would freeze your blood solid in milliseconds. These eruptions would release vast quantities of methane from deep storage, replenishing what's lost from the atmosphere. Cassini found the evidence. Mountains called Deux Monts and Gynaesa Macula that show every signature of volcanic structures. Sotra Patera, a massive depression that looks exactly like a volcanic caldera. Mohini Fluctus, a sprawling system of flow-like features that might be frozen rivers of cryolava. Between 2005 and 2006, infrared instruments watched parts of these regions suddenly brighten while everything around them stayed dark. Something was active, something was erupting. And there's chemical proof. Titan's atmosphere contains argon-40, an isotope that only forms from radioactive decay of potassium-40 locked inside Titan's rocky core. The presence of argon-40 in the atmosphere means something is bringing deep interior material to the surface. Cryovolcanism is the only process we know that could do it. But we still haven't proven it's happening right now. The methane mystery remains partially unsolved, hanging over every conversation about this moon like a dark cloud. And that mystery is just the beginning of Titan's impossibilities. Let me tell you why this moon's atmosphere alone defies every rule of planetary science. More than 150 moons orbit planets in our solar system. Only one has a thick atmosphere. One, Titan. And not just thick, Titan's atmosphere is denser than Earth's. Stand on Titan's surface and you'd experience 60% more atmospheric pressure than standing at sea level on our planet. It would feel like swimming 15 meters underwater. But Titan has only 2% of Earth's mass. Its gravity is pathetically weak compared to our world. By every law of physics we understand, Titan should not be able to hold on to this atmosphere. The gas should have escaped into space billions of years ago, stripped away by solar wind and Saturn's magnetosphere. Yet, it didn't. The atmosphere extends 10 times higher than Earth's, reaching nearly 600 kilometers into space, a massive envelope of gas that somehow refuses to leave. The composition is just as bizarre: 95% nitrogen, 5% methane, with traces of organic compounds that shouldn't exist together at these temperatures. Nitrogen is heavy enough to stick around, but methane? Methane should escape rapidly, lost to space over mere millions of years. Yet Titan's kept its methane for billions of years, replenished by some unknown source we're still trying to identify. How did this atmosphere form? Why does it persist when no other moon has anything remotely similar? Scientists analyzing nitrogen isotopes found ratios that match comets from the Oort cloud, icy bodies orbiting at the edge of the solar system, 5,000 to 100,000 astronomical units away. This suggests Titan's building blocks formed in the same primordial disk that formed the Sun itself, not in the warmer region that birthed Saturn and its other moons. Titan captured its nitrogen from ancient material, then slowly converted it from ammonia ice into gas over billions of years through impacts and cryovolcanism. But that's just our best guess. The truth is, we have no definitive explanation for why Titan's atmosphere exists. And that atmosphere is doing something that might be the most important discovery in planetary science. Christian Huygens first spotted Titan through a handmade telescope on March 25, 1655. Just a fuzzy orange dot orbiting Saturn. For over 3 centuries, that's all it remained. A mysterious blur that even our most powerful telescopes couldn't penetrate. Then Pioneer 11 flew past in 1979 and confirmed what astronomers had suspected since 1907. Titan had an atmosphere, a thick one. Voyager 1 followed in 1980, measuring density, composition, temperature, and mass. But the camera saw nothing through that impenetrable orange haze. The surface remained completely hidden. When Cassini finally arrived on July 1, 2004, equipped with radar that could pierce the smog, what it revealed made headlines worldwide. High in Titan's atmosphere, sunlight and energetic particles were tearing nitrogen and methane molecules apart. The fragments were recombining into ethane, propane, acetylene, hydrogen cyanide, benzene, at least 17 different organic compounds identified so far. But these reactions didn't stop there. The molecules kept combining, growing larger and more complex, eventually forming the tholins that give Titan its orange color. This is prebiotic chemistry, the exact kind of reactions that might have occurred on early Earth before life emerged. In April 2013, NASA confirmed that complex organic chemicals called tholins likely form on Titan based on atmospheric simulations. In June, scientists detected polycyclic aromatic hydrocarbons in the upper atmosphere, ring-shaped carbon molecules that are crucial building blocks for even more complex organic chemistry. In September, Cassini's infrared spectrometer detected propene, marking the first time this molecule had been found on any world beyond Earth. But the most shocking discovery came in 2017. Cassini detected negatively charged molecules called carbon chain anions, linear molecules that scientists believe acted as the basis for the earliest forms of life on Earth. This was the first unambiguous detection of carbon chain anions in any planetary atmosphere beyond our own. The data showed these chains becoming depleted near Titan's surface, while larger aerosol molecules underwent rapid growth. The chains were seeding the larger molecules, the same process that occurs in the interstellar medium between stars. We discovered a universal mechanism for producing complex organic molecules, happening right now on a frozen moon a billion miles away. And then, all of this organic material falls from the sky. It drifts down through the atmosphere, settles on the surface, accumulates in those coffee ground dunes, mixes with methane rain, collects in the lakes and seas. That's when things get genuinely strange. In 2014, Cassini's radar spotted something impossible in Lygium air. Bright spots appeared on the surface of the liquid methane, features that appeared and disappeared without warning, sometimes hours, sometimes weeks. Scientists called them magic islands. Similar features appeared in Krakenmare. These were the first confirmed instances of active surface processes in Titan's lakes. But what were they? Waves generated by wind, suspended particles in the liquid, nitrogen bubbles rising from the seafloor? Research published in 2025 suggests the most likely answer is floating icebergs made of organic material. The organic particles raining from Titan's atmosphere are highly porous, like Swiss cheese. If the porosity is between 25 and 60%, these particles can actually float on methane-ethane seas, despite being denser than the liquid itself. But there's a problem. Methane has extremely low surface tension. Liquid wants to seep into pore spaces immediately. For these particles to float long enough to explain the magic islands, they need to be several millimeters in size or larger, and the liquid must infiltrate slowly enough that they stay afloat for hours or weeks. Laboratory calculations show this is possible if the pores are structured correctly. Capillary forces can slow liquid infiltration, turning these particles into sponges that take time to absorb methane. Eventually, the pores fill completely, density increases, and the particle sinks to the bottom. This would explain why magic islands are transient. They appear when chunks of organic material break off from shorelines or islands, float for a time, then sink. Like watching glaciers calve on Earth, except these glaciers are made of organic compounds and they're floating on seas of natural gas. The existence of this floating material might also explain another mystery. Titan's lakes are unnaturally smooth. Wave heights rarely exceed a few millimeters. If there's a thin layer of floating organic particles covering the surface, it could dampen wave formation like oil on water, creating the eerie calm that Cassini observed. But this raises a question that's been haunting planetary scientists for years. If organic material is constantly raining down onto Titan's surface, why isn't everything buried under meters of sediment? Titan is 4.6 billion years old, the same age as our solar system, yet its surface appears to be only 100 million to 1 billion years old. We know this because Titan has very few impact craters, and the craters it does have are shallow, eroded, partially filled in. Something is actively reshaping Titan's surface. Something is erasing the evidence of ancient impacts. On Earth, water erodes mountains, wind carves valleys. Plate tectonics recycle the crust. Titan doesn't have plate tectonics, at least not like Earth, but it has methane rain that erodes ice, rivers that carve channels, winds that blow organic sand across equatorial regions, building and reshaping those massive dunes, cryovolcanism that might resurface areas with fresh ice. And there's evidence of something even more dramatic. Mountain ridges on Titan are concentrated near the equator, oriented east to west, linear to arcuate in shape. They resemble terrestrial fold belts that form from horizontal compression. Some scientists believe these ridges indicate global contraction. As Titan cooled over billions of years, its interior shrank slightly. The ice shell thickened, and regional uplift created the ridges we see today. The surface is remarkably diverse. Bright regions and dark regions. Xanadu, a reflective equatorial area the size of Australia, filled with hills and cut by valleys and chasms. Dark lineaments crisscrossing terrain that could be tectonic features or ancient methane stream systems. Northern and southern poles dominated by seas and lakes. Equatorial regions covered in vast dune fields. Mid-latitudes with radar dark uniform plains that appear younger than most major geological features except the dunes. All of this suggests Titan is not a dead world. It's active, dynamic, constantly changing. But the most remarkable thing about Titan's surface might be what it could become. When organic material lands on Titan's dry ice surface, it accumulates. Over time, these deposits react with each other, potentially forming what scientists call cryominerals, co-crystals of different organic compounds mixed together in ways we've never seen. If organic material lands in the methane lakes, most compounds have limited solubility and either float or sink depending on porosity and density. But there are transient environments on Titan where water and organics can interact. Impact events generate tremendous heat, ice melts. Water exists in liquid form for hundreds, maybe thousands of years before refreezing. cryovolcanic eruptions create similar environments. Liquid water mixed with ammonia flowing across the surface, cooling slowly while organic material from the atmosphere mixes in. And when organic material mixes with liquid water, chemistry happens that should terrify and excite every biologist on Earth. Laboratory experiments have shown that when Titan-like organic compounds mix with water, they produce amino acids: glycine, alanine, aspartic acid, gamma-aminobutyric acid. These are the building blocks of proteins, the fundamental components of life as we know it. One particularly important pathway involves molecules called aminonitriles. When aminonitriles mix with water containing ammonia, they undergo alkaline hydrolysis, producing amino acids. If Titan's impact melt pools or cryovolcanic flows contain at least 5% ammonia, and if aminonitriles are present in Titan's organic aerosols, then amino acid synthesis isn't just possible, it's likely. Research published in 2025 showed this reaction proceeds even at extremely cold temperatures, as low as -22 degrees Celsius. The reaction is slower, but it happens. After 6 months at 3 degrees with 5% ammonia, conversion rates reached 40% for alanine. At warmer temperatures near 21 degrees, conversion reached 80%. This means if Titan has impact melt pools that stay liquid for months or years, amino acid synthesis is not just possible, it's inevitable. But amino acids aren't life. They're molecules, complex, organic, essential molecules, but not alive. The real question is whether Titan's environments could support actual living organisms. Titan's surface temperature is -179 degrees Celsius. At that temperature, all biochemical reactions as we understand them would proceed impossibly slowly. Water is frozen solid, unable to act as a solvent for biological processes. Life as we know it cannot exist on Titan's surface. But Titan has that subsurface ocean, liquid water 35 to 50 miles beneath the ice, potentially harboring salts and organic molecules at temperatures that might allow biochemistry to occur. If life exists on Titan, that's where it would be, deep beneath the frozen crust in dark water, fed by chemistry happening at the boundary between the rocky core and the ocean above. It's a familiar story. We suspect the same thing about Europa and Enceladus. We know Enceladus has a subsurface ocean because Cassini flew through water plumes erupting from cracks in its ice, detecting salts, organic molecules, and molecular hydrogen, all ingredients that could support microbial life. Titan's subsurface ocean is similar, potentially habitable, completely inaccessible with current technology. But there's another possibility, one that's far more speculative but equally fascinating. What if life could exist in methane lakes on Titan's surface? It would have to be radically different from Earth life. It couldn't use water as a solvent. It would have to use liquid methane or ethane instead. Scientists have proposed theoretical biochemistry based on this idea. Organisms that inhale hydrogen instead of oxygen, that metabolize acetylene instead of glucose, that exhale methane instead of carbon dioxide. In 2015, researchers modeled a hypothetical cell membrane capable of functioning in liquid methane at cryogenic temperatures. They called it an azotosome, a combination of azote, French for nitrogen, and liposome, a type of cell membrane on Earth. The azotosome would be composed of small molecules containing carbon, hydrogen, and nitrogen, with the same stability and flexibility as phospholipid membranes on Earth. This is pure speculation. No one has ever observed an azotosome in nature, but the fact that it's theoretically possible means we can't completely rule out surface life on Titan. In 2010, scientists detected unusual patterns in Titan's atmosphere that could theoretically be explained by methanogenic life. There was greater abundance of molecular hydrogen in upper atmospheric layers compared to lower layers. Hydrogen was disappearing near the surface. There were also unusually low levels of acetylene on Titan's surface. If methane-based life existed and was consuming hydrogen and acetylene as energy sources, this is exactly what we'd expect to see. But as the researchers themselves noted, other explanations are far more likely. Surface chemistry we don't understand, catalytic reactions involving minerals, unknown physical processes. Even so, the possibility remains. If life evolved on Titan independently from Earth, it would be the most alien life imaginable. Nothing like Earth biology at all. A completely separate origin. And that would answer one of the most profound questions in science. Is life a universal phenomenon, or is Earth unique? Titan could tell us. NASA's Dragonfly mission is scheduled to launch in July 2028. It will arrive at Titan in the mid-2030s. Dragonfly isn't a rover or a lander, it's a rotorcraft, a nuclear-powered octocopter drone that will fly from location to location across Titan's surface. This is possible because Titan's thick atmosphere and low gravity make flight relatively easy. The atmosphere is 4 times denser than Earth's. Gravity is 1/7 of Earth's. A helicopter can stay aloft with far less power than it would need on Earth or Mars. Dragonfly will explore Titan's equatorial dune fields. It will sample organic material, analyze chemistry, search for prebiotic molecules, and potentially even biosignatures. The primary landing site is near Selk Crater, an impact crater about 90 kilometers in diameter. Impacts generate heat. They melt ice. They create temporary liquid water environments where organic chemistry can occur. If amino acids formed on Titan, Selk Crater is one of the most likely places to find them. Dragonfly's mass spectrometer will detect amino acids at extremely low concentrations. If they're there, we'll know. But even if Dragonfly doesn't find amino acids, the mission will revolutionize our understanding of Titan. We'll finally have detailed chemical analysis of the surface. We'll know what those organic dunes are made of. We'll understand how methane moves through the environment. We'll see cryovolcanic features up close. And maybe we'll solve the methane mystery once and for all. Beyond Dragonfly, other missions have been proposed. Submarines that could explore Ligeia Mare, balloons that could float through the atmosphere for months, landers that could splash down in northern seas and float while investigating the hydrocarbon cycle. None of these missions are funded yet, but the technology is being developed. Titan is too fascinating to ignore. And in July 2025, NASA researchers published a study showing that cell-like compartments, called vesicles, needed to form the precursors of living cells, could form in Titan's lakes. The study suggests liquid hydrocarbons might allow molecules needed for life to assemble in ways we've never seen before. Understanding this process could shed light on how life emerged on Earth, and whether life could emerge in completely alien environments. Titan is more than just a moon. It's a natural laboratory where chemistry happens in conditions that might resemble early Earth or that might represent something entirely new. So let's return to the beginning. Why shouldn't Titan exist? It's too small to hold such a thick atmosphere, yet it does. It's too cold for complex chemistry to occur on its surface, yet it does. It shouldn't have enough internal heat to drive cryovolcanism, yet evidence suggests it might. It shouldn't have a methane cycle that mirrors Earth's water cycle, yet it does. It shouldn't have organic chemistry that produces amino acids when mixed with water, yet it does. It shouldn't have floating icebergs made of organic material on seas of liquid methane, yet it might. Every time we study Titan, we discover something that challenges our understanding of how planetary bodies work. When Cassini completed its mission in September 2017, it had spent 13 years observing Saturn and its moons, 127 close flybys of Titan, thousands of images, and gigabytes of data. That data showed us a world that operates by rules we're still trying to understand. A place where methane plays the role that water plays on Earth, where water ice is bedrock, where organic compounds fall like snow, where chemistry builds molecules of staggering complexity in an atmosphere thick enough to see through. It's a world that feels familiar and alien at the same time. Landscapes that look like Earth, but made of materials that would be toxic or frozen solid on our planet. And beneath it all, there might be an ocean warm enough for life, rich enough in organic chemistry to support biology, completely hidden from our view. We don't know if life exists on Titan. We might never know without drilling through 50 miles of ice. But we know Titan is one of the most promising places in the solar system to search for life. Not because it's warm, not because it has liquid water on the surface, but because it has chemistry. Endless, complex, exotic chemistry that produces the building blocks of life everywhere we look. Titan teaches us that habitability isn't just about being in the Goldilocks zone. It's not just about liquid water and comfortable temperatures. Habitability might be about having the right chemistry, the right energy sources, the right molecules, and the right environment. And Titan has all of that in ways we never expected, in forms we're only beginning to understand. Nothing about Titan should exist. It defies our models, it breaks our rules. And yet, it's there, orbiting Saturn, wrapped in orange haze, covered in methane seas, filled with organic molecules, waiting for us to understand it. Cassini has been gone for over 8 years now. Its final mission was diving into Saturn's atmosphere, sending back data until the very end before burning up on September 15, 2017. The Huygens probe is still on Titan's surface, silent and frozen, the first and only human-made object ever to land on a moon in the outer solar system. Dragonfly is being built right now. Components are being tested, software is being written. In less than 2 years, it will launch toward Titan. Roughly 8 years after that, it will arrive. What will it find? We think we know some of the answers, but Titan has surprised us before. Every mission to Saturn has revealed something unexpected about this impossible moon. Maybe Dragonfly will find amino acids preserved in impact melt. Maybe it will detect signs of active cryovolcanism. Maybe it will sample materials we've never encountered before. Or maybe it will discover something we can't even imagine yet. Something that redefines our understanding of what's possible in the solar system. Because that's what Titan does. It shows us the universe is stranger and more interesting than we thought. It shows us moons can have atmospheres thicker than Earth's, that organic chemistry can happen at temperatures that would freeze carbon dioxide solid, that methane can rain from clouds, fill seas, and evaporate back into the sky. It shows us worlds don't have to follow our rules. They follow the laws of physics and chemistry, and those laws allow for things we never predicted. Titan exists despite everything that says it shouldn't. And that's the most important lesson of all. The universe is full of impossible things. We just haven't discovered most of them yet.